All right. So if you search for Google Colab and then you click the first one, and that's the one. And then if you've downloaded the Python notebook that I uploaded last night on Classum, and also in KLMS, if you know where it is, then please upload your notebook. You can go here, upload, and then choose file. And then for me, that would be like this. All right, if you haven't downloaded the practice notebook, please go to KLMS or Classum, and I've uploaded them on both places. All right. Is there anyone who hasn't opened the notebook on Colab? Okay. Okay. Or if you have your Jupyter notebook, it's fine. I mean, it's either Colab or Jupyter notebook. Yeah, exactly. Yeah, you can go with Jupyter notebook as well. I've actually written the code on Jupyter notebook, so it doesn't really matter. All right. Do you need more time? Done. Okay, done. Oh, okay. Let me see. So you go to research, Google Colab. Okay. Anyway, you go to Google Colab, and then you go. This is the first screen that you'll see. You go to this tab, upload, and then you choose file, and then you upload the one that you downloaded last night or right now. Yeah. Oh, okay. That's also a good idea. Okay, I'm gonna get started because we've already missed about 10 minutes, and I actually prepared a lot of quiz, but I guess we will have to skip some of them. And by the way, if you haven't muted your mics, please do. Actually, let me mute all of your guys' mics. All right. Okay, so if you've never used Colab before or Jupyter Notebook, it's the same thing, but it's a Python interpreter that is online. So well, I mean, if you know Python, if you ever use Python, actually, let me also share another screen of mine. So this is very, very preliminary, but if you go to a terminal, like whether you're on Windows or whether you're on Linux or Mac, there's a terminal and you go there, and then you type Python, and then this is how you can actually call up the Python interpreter, and then you can do like a very simple stuff here, 2 plus 3, or a equals 2, then a plus 2, 4, something like that. And then if you want to define a function, or if you want to do something like more complex, then it is really hard to use the interpreter. So that's where the text editor comes up. And then when you use text editor, you have to actually write everything here. You can just, you can't execute your part of your code and see if it's working. You can't do sanity check. 그 화면을 어떻게 넘어가는 건가요? 요거는 지금 그냥 제 예제인데, 이건 그냥 뭐 전혀 신경 쓰실 필요 없어요. 이건 그냥 제가 예제를 보여드리는 거라서. Don't mind this black screen. This is just an example. This just to encourage why using either Jupyter Notebook or Colab is a good idea. So either use Atom or I forgot the famous one. Either use Vim or whatever, just any text editor, or maybe advanced IDEs. It's really not really easy to execute a single function that you've just written for sanity checks. So that's why using Notebook is a way better idea. I mean, at least for me. So like this, like if you have a notebook and then you have this, a notebook consists of cells. So within a cell, you write a code and then you run it with Shift Enter. Right. And then that's how you load up Numpy. So I'm not gonna explain the syntax of Python, because I've already said that you need to know how to write Python code. So I'm not gonna go through the syntax or anything. So okay, so you load up Numpy, and then this is just some basic things that I've written just to make the tutorial easier, or make the practice easier. So you do that, and then let's go to cell number 4, this one. So this is the very first thing that we'll do in this practice. So if you've never used NumPy before, then please note that this is no different than MATLAB. If you've never used MATLAB, then I guess it'll be a bit tricky. So if you've used MATLAB at least once in your life, then you know what you're gonna do. This you can think of NumPy as a MATLAB for Python, because the syntax is very, very similar. Like how you define a vector, how you define matrix, and how you like transpose a matrix, and how you do like math operations. It's very, very similar. But if you've never ever used MATLAB before, then think of NumPy as a Python library that makes it really easy for you to do math operations, especially linear algebra, like matrix operation, like matrix multiplications, dot products, or inversing a matrix, or solving your linear systems, something like that. It's basically a fundamental tool for all data science. So of course. So as I said, if this is MATLAB from Python, then you can define a scalar, or a vector, or or a matrix, or even more actually. So let's start with scalar, vector, and matrix. You go to the next one, you go to the next cell, and then if you run this, then you can see how they are printed out. So I'm using this print object function that I defined earlier. So it's just printing an object with a title on top. So this is a scalar, this is a vector, this is a matrix, and then there are some property functions, or property member variables, such as like ndim. This if you run this, then you can see that the number of dimensionality, or the number of axes, or so it's if it's a scalar, there's no dimension, so it's 0. If it's a vector, then the number of dimension is 1. If it's a matrix, then there is a row and there are rows and columns, so it's ended 2. And this shows you the actual shape. So a vector, a scalar doesn't have shape because it doesn't have a dimension. A vector, it has 3 elements, so the shape is 3, and a matrix has how many? It has 2 columns and 3 two rows and 3 columns, so it's 2 by 3 matrix. And you can actually use shape as a value. So if you go like, sorry, you print shape 0. If you print shape 0, then you get the first element. And you'll be using this a lot when you use PyTorch. Like if you have a matrix, or if you have a data set and then you don't know the size of the data set, then you have to type the shape and then get like some dimension to do some operations in the downstream task. So, all right, so this is pretty easy. So nothing too complex. Now we move on to tensors, which is n-dimensional array. So this was like 1-dimensional array is called vector, 2-dimensional array is called matrix, 3-dimensional or 4-dimensional, we call them tensors. So you run this, and then you can imagine what kind of shape they will have. So it has like this alone here, this much is already a matrix, but has 2 matrices inside, right? Because it's a list of lists. So it has 2 matrices inside. So it's D is probably a 3-dimensional matrix or 3-dimensional tensor. And the same logic, if you apply the same logic, then E would be 4-dimensional, right? So you can actually print them out and see this is a tensor. So it has a matrix, 1 matrix, and another matrix. So it has 3 dimensions with shape 2, 2, 3. So it has if you draw this, then it would look like this. So it has a 2 by 2 by, right? Two by 2 by 3. Right. So this is how it looks, and it has what's the value? It's 1, 2, 3, 4, 5, 6, 7, 8. So it's 1, 4 here, and then 7 and 10 here, right? So it'll look like this, and then like following value this 4, 5, and 6. So 3-dimensional tensors are easy to imagine. Not so much for 4-dimensional. Anyway, so yeah, it has 2, 2, 3, and then if you look at this, then it has it has a tensor here, a 3D tensor here, and another 3D tensor here. So it's 4-dimensional, and the shape is 2 by 2 by 2 by 3. So it has like, so it means that this dimension says that there are 2 by 2 by 3 tensors, and this dimension says that there are 2 by 3 matrices. Any problem with my mic? 소리 혹시 안 들리시나요? 오케이. 안 들리시는 분은 컴퓨터에 조금 문제가 있으신 것 같은데, 네, 일단 진행을 하겠습니다. 네. All right, so quiz, the very first quiz. So what is the shape of a tensor that looks like this? And all the quiz, you can actually write them, and then you can execute them to see. Okay, that was very fast. Okay, usually I would, give a bonus score or something to the first responder, but this is a pass or fail class, so there's not really a bonus that I can give. If it was an offline class, maybe I could give you a chocolate or something. Sorry about that, but yeah, the 2 by 3 by 1. Actually, yeah, just to show to other people. Okay, A equals np array. So there should be 1, 2, 3, 1, 2. Okay, one more. Yes. Yep, 2 by 3 by 1, exactly. All right, so like this, I have I have a lot of quiz down the road, but and of course there's no solution there, but you can always just copy paste and see what happens. So let's move on. So this was the basics of like how you define a tensor, how you define matrix, and like how you get the shapes and the number of dimensions. So there are better ways to define especially tensors, because when you want to like define a high dimensional tensor, like 4-dimensional, 5-dimensional, 6-dimensional, you don't want to actually type this all the time. So there are better ways to define a tensor, which is this. So if you want to define tensors of all the ones, okay, the question, what happened if I change it to like this, uneven number of elements in the list? Yeah, that won't work. Actually, you can just try that. If we're talking about lists, then it won't be a problem, because that's just Python list. I think you can have uneven number of elements in the Python list, but if you want to make it into matrix, then it probably won't work. But we can try that out like this, and then we can try to. Oh, it does work. Okay, so it becomes a list. So it's not a proper NumPy n-dimensional array. So if you had a proper form, then the type of A is a class is NumPy ND array. So this is a proper matrix or tensor. So you can do like fun stuff like a dot product or like linear algebra or something like that. But if you have a uneven number of elements and then I'm sorry, this is not uneven number of things, and then you define it, then inside the NumPy array, there will be list, which is Python list, right? So it's not a proper matrix, and you can't do dot products with this. You can't do matrix inversion. You can't do transpose because it's not a proper matrix. But I guess, yeah, you can at least define it like this. All right, so if you want to define a matrix filled with ones, then you can go like this. So ones, and if you want 10 elements, you get the 10 elements. You can actually do better than that. You can have a 2 by 5 matrix filled with zeros. Looks like this. And then if you want a 2 by 5 matrix filled with 5s, then you can use the full API. So, and then if you wanna just some random matrix where the dimension or the shape is 2 by 3 by 4, then you can go like this. And note that random is you get any number between 0 and 1. So 0 inclusive. So starting from 0 until like 0.999999 like that, you get a random number. It's a uniform distribution. So, and you can use like normal, or there are a lot of distributions in the random package. So this is NP random, and inside random there are a lot of fun APIs you can play around with. We will use this throughout the tutorial or throughout the practice. So please keep a look on it. So arrange is starting from 0, you get the number of elements that you wanted. So starting from 0 to 9. So it's basically just a list of counting numbers. And you can, if you define a matrix with arrange, it'll always be an integer matrix or integer tensor. So you want to change that to a float. So this is how you do it. So you just put as type and then anything that you want, float, int, boolean, or bool. It doesn't really matter. You can do whatever you want. So it's become 0 to 9, 0 point. Yeah, you can see the point here, the dots, to show that this is a float value. And then one other trick that we need to learn before we go on is the reshape API. So arrange will never give you anything other than actually a list or a vector. But when you want to reshape it into a matrix or tensor or whatever, then you need to call this function a reshape function. And then if you just put dot reshape and then just put in the number that you want, so it'll become a 5 by 2 matrix like this. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we will use arrange all the time throughout this practice session. All right, so I guess you can try out how to do this within, I don't know, 30 seconds or something. create a 4x3x2 tensor filled with 0 to 23, all float values. Can you do that? Right, exactly. Oh, 23 random is not exactly what I required, because I was hoping that you would use arrange. But you could get the same shape by doing what you did. 경현님, 네. Actually, yeah, you can do the same thing. I guess the specs of the quiz was not very specific. All right, moving on. Why are there 6 cells hidden? Yeah. So yeah, this is a bit lengthy because this is a very important subsection, indexing and slicing. You will use this all the time when you write PyTorch code or TensorFlow code, whichever framework that you'll be using in the future. But at least in this practice session, we'll use PyTorch all the time. So indexing and slicing is it's an essential part of NumPy. So let's go with a very simple example first. I guess this is a bit lengthy. So let's see. Before we actually hit the execute button, let's see what would happen if we actually hit the execute button. So here we're defining a 10-dimensional vector, and then let me just comment them all out so that we don't get too much thing all at once. Right. So first we define a vector, and then what we did is accessing the first element, the second element. So first element, second element, obviously 0 and 1, and there's a minus index. So -1 and -3. That means you go from the back. So -1 is the last element. -3 is the third from the last. So it's 9, 8, 7. So 7, right? So that's how you get that's how you use the negative index. So we'll comment them out. Can I say something like GDB in Python? There's actually PDB in Python, so it's a Python debugger. You can import PDB and then set a trace so that at some point, like a breakpoint in GDB or in Microsoft Studio. In Colab, I'm not really sure why you don't actually need the PDB in Colab, because you can break everything down into cell level. You can write a piece of code in some cell and then execute and see what happens, and then check its variable in the next cell, and so on and so forth. But I'm not sure. Yeah, I've never tried using PDB in Colab or in Jupyter Notebook, but I guess you can, because it's still a Python library, so you can import anything. 3.배열이 화면에 디스플레이 될 때 MATLAB과는 조금 다른 것인가요? Actually, it's been so long since I've used MATLAB before. I guess it's been at least 15 years, so I can't really tell how different it is. 어떻게 다른가요? Samso. I'm not sure what that really means. Is that the shape of a tensor? 곱하기 4가 같은 듯. 준우님 계셨군요. Dimension 3, 4, 5. I can't really see how that would be different. As long as you understand what's going on in NumPy with respect to the printing and stuff, I guess we're fine. Yeah, there must be some differences between MATLAB and NumPy, but yeah, as long as you understand what's going on, probably doesn't matter. And this is slicing, but we're starting with a very, very kind of unuseful slicing. So actually, if you use a if you use a column, and then the first part is the starting index, and this is the last index. So if you access all of the elements starting from 0 till the end, till the 10th element, but exclusive. 10 is not included, so it'll be the actual elements will go to the 9th element. So let's just see what happens. Let's just see what happens if we just print this out, and then see if there's any difference between the 4. So this is A 0 to 10. This is A 0 to blank. This is A from blank to 10. This is A blank to blank. So the column here defines the range of your sub elements, and this is start to end, and you can see that there's no difference between all these 4. So you can see that implicitly, if you use a blank, then it means that it's either starting from the 0 and going till the end, right? So this is pretty obvious. And then, so what would happen here then? This obviously means we want everything from index number 7. So you can imagine it would be 7, 8, 9. This will access elements. I said that blank means 0. So this is 0 from 5. So it'll go to 0 to 4. I mean, so I said that this is exclusive. So 5 is not included. So it'll go to the 4th element. And 2 to 5, so it's even a shorter one. So it'll have only 2, 3, 4, 3 elements. So if you run this, you can see exactly what you get. 7, 8, 9, 1, 2, 3, 4, 0, 1, 2, 3, 4, and 2, 3, 4. All right, moving on. Also quiz. What is A minus 4 colon? Right, okay, so very fast. Okay, some of you already know Numpy, some of you are very familiar with it. And next one, blank till -8. That would be 0, 1, 0, 1. Okay, so there are 2 different opinions. 2, 3, 4, 5, 6, 7, 8, 9, 0, 1. Why? We can actually try them out. We can always try them out, actually. So print a -8. See what happens. It's 0, 1, because -8 is like the 8th element from the back. So it's 9, 8, 7, 6, 5, 4, 3, 2. So, and 2 being excluded. So it's 0, 1. All right. Now let's just see what happens actually. So we've added one more thing here. So previously it was just 0 to 10, but now we have another colon and 2, and see what happens. So this is 0, 2, 4, 5, 6, 8. So it means that if you use 2 here, you are skipping every other element. So it's 0, 2, 4, 5. If you use 3 here, you're skipping all. So you're accessing every 3 elements. So if you use 2, you're accessing every other elements, and then. So you can see that if you use 2, 6, 3, then you are starting from 2 because it was 2 here, and then the end is 6. So this will be not included, and you're accessing every other 3 elements. So it's 2, 5, and the next one would be of course 8, but that's beyond the range. So it's 2, 5, and you can go a bit overboard with this idea. -1. So if you use -1 in the back, you can imagine what would happen. Oh, this is efferent. You're accessing it from backwards. So -1 means 9, 8, 7, 6. Sometimes you need to use -1 when you're writing like deep learning codes. And because you're using -1, you should start from the higher index to the lower index. So this would be 8, 7, 6. But without the -1, what would happen? Starting from 8 and going to 5. It would be empty because there's nothing inside, because you're starting from a higher index and you're trying to reach to the lower index. And you can see that if this is what's -1, then you get a value, but this is obviously 1 here, and then you don't get anything, right? Can you get 963 using A? Knowing that A is 0 to 9, can you get 963? Oh, there is actually two interesting expressions. Let me just get the first two. This here. I'm sorry, this should be 9. This here. Will they be the same? Yeah, they are. It's because -1 is the last element. And wait, let me see. I guess the index was a bit different. Doesn't really matter because whether you go towards the first or whether you go towards the second, it doesn't matter because you're skipping every 3 elements. So it doesn't really matter. Yeah, there can be a lot of different answers because there's a lot of different ways to access or slice your vector, right? A9 is 8. Actually, A9 is 9. Yep, A9 is 9. All right, moving on. So that's all the index and slicing that you need to learn, and it's just applying it to higher dimensions. So if you have a matrix, then you go like this. So if you have a 3x3 matrix, and there are 2 different ways to access an element. This is actually a C style element, C or Java style accessing. So this is a first array and then the second array. So first dimensional array, second dimensional array, and this is exactly the same as 0.0. And 1.1 would be 4. So 0.0, 1.1, 2.2, 2.0, 0.2, you know. Okay, so about a bit more quiz. Actually, there are 3 quizzes. So how to access the last row? Can you get a guess? The last row meaning 6, 7, 8. How do you get 6, 7, 8 out of? Okay, so again, two different answers. Oh, I didn't know that this would work. Let me actually try that out. That's interesting. Let me try that out. Oh, yeah, it does work. Okay, I've never tried this before. This is interesting. Yeah. Yeah, this is okay because this is my -1 mean the last row. Of course, you can go 2, also means the last row. So that being said, how to access second column? I'll just go right ahead and give you the answer. So the second column would be you want all the rows, and then you just want the second column. So you go like this, and that's how you get 147, right? 147. Let me just comment these out. 147. How to create 8, 5 using A. How to create 8, 5. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and then you want to create 8, 5 here. So that would be like a subsection of your last column. That was very fast. So let's see how Tonghyun Gok did it. So you get the last column, and then once you have the last column, you skip. Okay, you skip it. Oh, okay, the last column, and you start going backwards. So that would actually be correct. So let me see if that works. By Hangono. That also works. How does that work? So it's 2 by 0 by -1. So you get, oh, you invert. Okay, you inverse the rows. Okay, so inverse the rows, but you inverse the row, but you start with actually no. Oh, okay. So inverse the row, and then you get only you go to only the second row. Okay, so I guess yeah. Okay, so this should have been if this was -1, then this is inverting row. That doesn't work either. That's interesting. Huh. Okay, so if you have nothing here, then that would mean inverting the row. If you have 0 here, that's excluding the first row, and then now you've inverted it. You only take the last one. Okay. Okay. So that's a bit complex, but that still works. That's okay. Yeah, as long as you get the result. But so since everybody's using different accessing methods, I guess we're getting to at least the practice is getting through to you. So that's good. So so we move on to this tensor, and this is we start with a 4x3x2 shape tensor, 4x3x2, filled with 0 to 23, because this is 24. And let's see, that's what happens. So it looks like this. So it's 4x3x2, and then you're accessing the third matrix, first row, second row, first column. So that's a third matrix here, and then it's the second row here, and then you're getting the first column here. So that's 14. So you get the 14, right? So it's a bit complex, but yeah, as you go more high dimensional, right? So okay? So the quiz. All right. So what would be A0? What would be A01? You can, since everybody already kind of knew how to access columns and rows, you can actually imagine. A0 would be the first matrix, right? We can print them out. A0 being the first matrix. Exactly, first matrix. Then A0, 1 would be, we're accessing the first matrix, and then what? We're accessing the second row, so that would be 2, 3, 2, 3, right? So we're all good here. Can you create 0, 2, 4, 6, 8, 10 from A? 0, 2, 4, 6, 8, 10. So we're only getting the first column here and the first column here from the right. Okay, so there's already an answer. Why that would be column 2, column 0. So column 2. So what's the first A column 2? That means that you want to access the first 2 matrices, right? Because 2 is the third element. So you want to access the first 2 matrices. So that's column 2. And then the second column is you want to access all the rows. So you want to access all the rows. And then the third 0 is that you want to access the first column only. So you're accessing only the first column, 0, 2, 4, 6, 8, 10. Actually, let me just print them out. Until here. Oh, until here. So we get exactly this. So we have this, and then if we want the first column only, then we just put the 0 here. That's how I get 0, 2, 4, 6, 8, 10. All right. Seems like everybody's following along. Moving on. So conditional indexing. This is sometimes this is useful, but it's just a kind of a trick. So if you have a 3x2 matrix and you have a conditional index, so conditional index being your index needs to look like, actually, let me just comment this out and then print index. What this would look like. So 0, 1, 2, 3, 4, 5, 4, 5, and the condition is that it needs to be dividable by 2. So it's modulo 2 operation. So all the even numbers would be true. So 0, 2, 4, true, 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 1, 3, 5, false, 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 right? Because odd numbers are not divisible by 2. So if you use this, actually if you use this in your matrix, what would happen? 0 to 4, because you're accessing only the true elements. So sometimes if you use like, if you use maybe condition, it can go this way as well. Oh, actually this doesn't work. I'm sorry. Yeah, we don't need this. So you only get the elements that are above 2, yeah, 초과. So that's like above 2. So you only get 3, 4, 5. Because it was 0, 1, 2, 3, 4, 5. You only get 3, 4, 5, and if you use this index to access the elements, then you get 3, 4, 5. So that's how you get. Okay, actually, I just solved my own quiz. Sorry about that. Yeah, but you get the idea. So it can be any conditional, any condition, any condition. It could be a modulo. It could be bigger or smaller, equal, whatever. All right. Moving on, taking specific elements from a vector. So this is it's a bit more advanced indexing. So if you have 0 to 9, and if you want to access only the first, third, and fourth element, then you just enter them in. So 0, 2, 3. This becomes a bit complex if you go to a higher dimension. So you have a 6x4 matrix. So let me just print them out first. If you have a 6x4 matrix, and you go like this. So you take you take all the rows, but you only take the specific columns, 3 columns. Let's see what that'll give us. Then it'll go like this. So you take all the rows, but you only take the first column, the third column, and the fourth column. So you're excluding the second column. So you'll get this matrix. What about the next one? It's the other way. So you get only 3 rows, but you get all the columns. And then this one goes a bit. All right, good. Now this is a bit different. So if you have a tuple that consists of a pair of coordinates or pair of indices, and you enter them into your matrix, you get a specific number. So let's see how that happens. So 0. So there are 4 elements in your first tuple, and there are 4 elements in your second tuple, and they become a pair. So 0, 1, 0, 2, 1, 0, 5, 3 becomes each index. So what is 0, 1 here? 0, 1 is 1, 0, 2 is 2, and 1, 0 is 4, and 5, 0, 5, 3 is this. So that's how you get multiple, like in arbitrary places. You can this can go up to like any arbitrary. You can actually have like more repeated indices here, repeated elements like this. Then you get 23 and 23. Yeah. And please do not confuse this with this. They look almost the same. See, they look almost the same. It's the same elements, but if you run them, you get very different results, because one was a tuple, the other is an n-dimensional array, and you just enter them in. And the question, 조건 index, so do conditional indices or accessing give you one-dimensional output all the time? Not really. So you can actually, you can, so take a look at this. So if you have a matrix as an index and then put them in, I mean, this is a tuple and this is a proper matrix. So if you put a matrix inside your matrix, it becomes a tensor. So if you can construct your matrix or your vector, whatever, if you can construct your indices with conditioning like this, then you can get the same output. So as long as you can construct any matrix or tensor indices with conditioning, then you can get the same output, right? It's just logically, that's obvious. So anyway, so yeah, please, do not confuse this between this and this. So they have the same value. It's just that one is tuple, what the other is. So let's see what happens here. What is happening here? 0, 0, 1, 5, 1, 2, 3, 1, 2, 0, 3. 0, 0, 1. This this corresponds to 0, 0, 1, 5, and this actually is the rows of the matrix. These are the rows of the matrix A. 0, 0, 1, 5. So 0, 0, 1, 5. So they become a matrix, and then 1, 2, 0, 3, 1, 2, 0, 3. They also become a matrix, and then you're putting them together, so it becomes a tensor. So okay, so yeah, there are two different ways to access multiple elements in your tensor, in your n-dimensional tensor. So please, actually the syntax might be a bit different in PyTorch, but there are always, but you can, yeah, just it's suffice to say that you need to remember there are two different ways to access elements in your n-dimensional tensor. Let me see. How about this way? Okay, this is a bit. Bring a comma here. Let's see if this works. 0, 1. Yeah, I'm not really sure. I'm just trying them out. I think we need this. Okay, they don't work. What have I done wrong here? Okay, I guess this doesn't work because this is not a. Yeah, I'm sorry, because this is not a proper matrix. So you can see that I'm trying to define an n-dimensional array, a proper tensor here, and the tensor cannot have weird values like this. But what you can do is you can transpose your matrix and then do the same thing, and we'll get to transpose in the 2 sections below. Yep, aha, yeah. Nice trick, right? Can you share your screen again? It's stuck. Okay. Is it okay now? Rushta Basir Ahmad. Yeah. All good? Can you see my screen now? All right, good. Moving on to the mathematical operations. So basic operations, so it's just 4 basic operations, addition, subtraction, multiplication, division. Okay, so before we go to something more advanced, let me just clarify that A and B, so A has 1, 2, 3, 4, 1, 0, 2, 3, 4, 0, 1, 2, 3, 4, 5, and B is a 3 by 2 matrix filled with 1s. So they are of the same shape. They both have the shape 3 rows, 2 columns, 3 by 2. So you can do you can do whatever you want with them. You can add them together. You can you can minus them together. You can multiply, divide, whatever, and they'll all work. So moving on. You will use these a lot of the time. So you define a 3 by 2 matrix, and then you let me see. You find 3 by 2 matrix, and the sum is that you want to sum everything in the element, so you get a 15. But if you use a specific axis, then you're summing along that axis. So axis 0 is a row, right? It's a row-wise summation. So 0, 2, 4 is 6, 1, 3, 5 is 9, so 6, 9, you get a 6, 9. Axis 1, this is going column-wise, right? It's going horizontally, so it's 1, 5, 9, so you get 1, 5, 9 here. Very easy, right? You can do more than just summing up. So you can do mean, max, or minimum. And you can do it for specific axes as well. But let me just give you an example what would happen. So mean means that you want to you want to get an average value of all the elements that you have inside your tensor. So it's 2.5. Maximum value is 5. Minimum value is 0. And you can get standard deviations, or you can get. I think there are a couple more unary operations, and if you use a specific axis, then you get what you see here. All right, quiz. Given a matrix or tensor of array tensor of shape 2, 3, 4, what is the mean of the sum with respect to the last dimension? Let's try it out. It'll be a specific number. It's a mean of the sum with respect to the last dimension. Mean of the sum with respect to the last dimension. So you need to sum with respect to the last dimension first and then get the mean. All right, let me see. Let's check that out. NP 24. 2 by 3 by 4, and then you get what you get for sum with respect to the last dimension -1. Then you get the mean. Wait, does that probably won't work? Let me see. But at least we can go over here. All right, so there you have the sum of the last dimension, and then you get the mean of the last dimension, that being mean of sum. Oh, is it just mean then? Oh, I'm sorry. Yeah, 46.0, exactly, right. All right, moving on. So this was simple, what was it? It's unary operations. We go to the dot products or inner products, I guess, yeah. I hope everybody's familiar with the dot products or the inner products, vector dot products. So here you have a 0, 1, 2 and 1, 1, 1, and then you do a dot product and you get what? 3, because it's 0 times 1 plus 1 times 1 plus 2 times 1, so it's 3, right? So that's easy. So vector dot products can be done with np dot here. But if you go to matrix multiplication, then I guess it's still the same. If you go to tensor, it's a different story. But if you go to matrix dot products, so you have a matrix of matrix A of size 3 by 2, 0, 1, 2, 3, 4, 5. And you have another matrix B filled with 1, shape 2 by 3. So that you can actually do dot products. So if you multiply A with B, then you get a matrix of shape 3 by 3, right? So that's all basic linear algebra. You can see here, you can use either np dot or you can use the et product, et operator. So this et operator is a matrix multiplication operator. So it's like plus and negative. It's plus like minus or star or division. It's a matrix multiplication operator. So if you have a matrix and a matrix, if you have there are two matrices, A and B, and if you do, you can go either way. You can go either dot or A at B. You get the same result, right? But if you go to tensor, so if you go to tensor, then it becomes a different story. So first tensor is 4 by 3 by 2 tensor, and the next one is 4 by 2 by 3 tensor. And what do we want to do here? What's happening here is that, let me just draw something here. So it's 4 by 3 by 2. Four by 3 by 2. And so this is A. And then there's what? There's 4 by 2 by 3. So 4 by 2 by 3. And what do we want to do here? A lot of times when you're doing deep learning, the first axis is the number of is the batch axis. So because you're doing mini batch update using stochastic gradient descent, so the first axis is usually a batch. So let's say that you have a batch of 2 by 3 matrices and batch of 3 by 2 matrices, and you want to do dot products with them, and you just want to do it independently. So you want to do it, sample by sample, because it's a mini batch. So there are 4 samples within your mini batch, and you want to do it sample by sample. So you want to multiply so that there are 4 rows here. 4, 3, 1, 2, 3, 4. Yeah, right. 1, 2, 3, 4. 1, 2, 3. So you take okay. So you take this one and you take this one and then do dot products, and then you take this one and this one, and then you do the dot product, and then you take this one and then this one and do the dot product, and then you want to get one. So if you do a dot product between the two, then this is a 3 by 2 matrix. This is a 2 by 3 matrix. So what you would like to get is some weird operations. Then what you would like to get is a 4 by 3 by 3. So 4 by 3 by 3, because you've done you've taken 3 by 2 matrices along the batch axis or the first axis, and then you did the dot product. So you get 3. If you do dot product between 3 by 2 and 2 by 3, you get 3 by 3, right? So it's a 4 3 by 3 matrices. So that's what you want to get. So if you want to do this, then if you want to do this, let me go out of here. If you want to do this, there are 2 options. There's either NP dot or there's A at B. And you can try out which one is the one that we want. So A is now it's a tensor. This is also a tensor. So A dot B gives you 4 3 4 3 shape, and A at B gives you 4 by 3 by 3 shape. So you know that you want to use this one, right? So the question is, if we go higher dimensional than 3 dimensions, then are all so except for the last 2 dimensions, are the remaining dimension, like if you have 4 by, so let's take a look at this example. So let's say that your tensor has a shape of 4 by 3 by 4 by 3, and the question by Hong Gi-yoon is that are these two 4 by 3, do they also represent batches? Not really, because batch usually there's only one axis for your batch, because you're doing batch mini batch gradient descent. So you only need to use one. You only need to assign one axis to use as a batch. But you can think of let's say that you have a matrix, and this is your time axis, and this is your batch axis. So like you have 4 samples of sequence length 3 4 by 3 matrices, something like this. You can go even higher than that. Like you can. There are a lot of opportunities for you to use higher dimensional tensors when you're coding in PyTorch. Another question by Trejinon. So it's okay. So I'll just address the first question, the last question first. So dot and add. So when you're using matrices, when there are 2 matrices, they give you the same result, because this is a matrix, this is a matrix. I mean, when I say matrix, I mean two-dimensional tensors. So when you use 2-dimensional matrices to do dot products or add, it's essentially the same thing. But if you go higher than that, if you go higher dimension, then A is a tensor, B is a tensor, 3-dimensional tensors, and they give you different results. So if you go higher dimension, you should use add most of the time. So what happens in here, A dot B, is, so the dot product so NP dot uses, so NP dot given A and B, what it does is it takes the last axis of A, which is 2, and it takes the second to the last axis of B, which is 2, and then do the dot products. So you have 4 3 2 and 4 2 3. So these 2 and 2 get erased because you do dot product. So that's why you get 4 3 and 4 3. So that's why you get 4 3 4 3. So I'm not really sure why NP dot is implemented like that. I guess there could be some uses. Actually add in matmul are the same thing. So NP matmul and A at B is the same thing. It's just a shortcut. So let me just write that down as well. Yeah, it's the same thing. And you can actually check if they have the same value. So print NP met mul A comma B equals A at B. See if that's true, and they are true. See, all true. All the elements are the same, so they're the same thing. All right, quiz. What would happen if we do 4, 3, 2, and 2, 3, and when we do dot products and met mul? Why don't you guys try these out? Try this out, and then I'll answer the question from Mario. Are there any performance difference between met mul and dot for 1 2D tensors? That's a good question. You can't use met mul for a 1D tensor because it's at least for matrix multiplication. Huh. That's a good question. I'm not really sure. You can time them using like, the time library. I would say there's very little overhead between very little difference between the two. If you're using 2D if you're doing met mul between 2D and dot between 2D tensors, I think it'll be essentially the same. Does this mean we need to use add operators when using higher dimension than 2? So when you want to do something like this here, what I've described in the figure, if you want to do something like this, then always use that operator. If you want to do something weird like np dot, I'm not sure what the use case would be, but there might be some use cases. Yeah, just remember that np dot is different. Why don't you try this one out? Why don't you do this with both np dot and add and see what you get, and you'll understand. Is B broadcasted? Wait, is that the quiz for everyone? 최은진님, is that a quiz for everybody or is it a quiz for me? How about four-dimensional matrix? I don't really understand what the question is. How about a four-dimensional matrix? 4 by 3 by 3. I just wanted the quiz. I just answered the quiz. Oh, B is broadcasted. Not really sure if that's true. 4차원의 경우엔 텐서가 어떻게 작동하나요? It's exactly the same thing. You need to, for example, I'm just gonna, let's say, you can just put 2 here and then go 2 times this. And this becomes 2 by 4. So this is a 2 by 4 by 2 by 3 matrix. And then you do np dot and a. I'll just erase this one. Let's see what happens. So this becomes 2 by 4 by 3 by 2 by 4 by 3 because the last axis and the second to the last axis is erased. So you get 2 by 3 by 4 and 2 by 3 by 4, except this one. So 2 4 3 2 4 3. And for the add operator gives you 2 4 3 3 because you take 2 4 2 4 as a like a something that you don't want to touch, and then you only use a 3 2 and 2 3 to do the matrix operation. So if you do this, so let's just try them out. I'm sorry, this is not. This should be 4 by 3 by 2. What happened here? Why are they the same? Why are they the same? Oh, I see what you mean. Okay, 최은진님. Okay, so I see what you mean. Yeah, the B was broadcasted. For add operator, B was broadcasted, but for np dot, that's not really true because you take the 2 and 2, and then you erase them, and that's how you get 4 by 3 by 3. So to see if that's true, actually we can try them out. not this one. Maybe, yeah. NP dot AB equals A and B. See if they're true. See if they're the same. So they're the same thing. So what is the meaning of broadcasted in Korean? I'm not really sure. We'll get to broadcasting, and there is a subsection called broadcasting. So we'll get to that. So basically, broadcasting은 그 차원 수가 안 맞아도, 그러니까 1차원으로 남아있으면 그 차원을 불려주는 거거든요. 그래서 그거의 예제를 이따가 볼게요. broadcasting은. Now, all right, so if it was broadcasted, actually, let me see if that's. I'm not sure if that's true. 은진님, I'm not sure if that was actually true. All right, so let me see. So A, B, and another C is 1 by 2 by 3. So one is NP dot, the other is A by C, if that's true. Oh, okay. So it was broadcast. Okay, so you're true. You're right. Unjin, you're right. So it was the B was broadcasted, assuming that there was implicit 1 here, and so NP. Okay. Until now, I didn't really understand what NP dot was doing when it was using higher dimensional tensor, but I guess it is the same thing as A at B. It's just implicitly broadcasting the second argument if the second argument 2 by 3. Right. Yeah. So what's happening here is so we have 4 by 3 by 2, 4 by 3 by 2. And we have what? We have 2 by 3, which is just 2 by 3. And you want to multiply, you want to do dot products with, there are 4 rows, 1, 2, 3. So you take this one and take this one and do a dot product. You do a matrix multiplication and you get 3 by 3 matrix, 3 by 3. You take this one and this one again, and then you get another 3 by 3 matrix. And then do it again and do it again, right? So that's how you get, this is a 3 by 3. Everything is 3 by 3, and you have 4 of these. So that's how you get 4 by 3 by 3 matrix. So that's what's happening here in this last quiz here. All right, so moving on. Shape manipulation. This is also a very often visited operator. You'll do a lot of reshapes and concats and stuff. Okay. All right, so reshaping. We've taken a look at the reshaping just before. So I just need to tell you just one thing. If you use -1, so before we move on, so it's a 2 by 3 by 4 matrix, 2 by 3 by 4 tensor, right? So it's a 2 by 3 by 4 tensor, and then you can reshape it into 6 by 4 because it has 24 elements. So it's okay to reshape to 6 by 4, right? But let's see what happens to B and C. So B looks like this, C looks like this, even though this was -1 instead of 4. So what's happening here is that if you use -1 when you're doing reshaping, it means that it'll automatically calculate it for you. Because if this is 6, this has to be 4 to get the shape right. So it's just, you know, leaving it to the expert. So if you go like this, 3 by 2 by -1, then it'll look like this. So 3 by 2 by -1. -1 needs to be 4 because there needs to be 24 elements. So you can see that the last dimension is 4 elements here. 4, 4, 4. Right. So quiz. What would be this? What would D equal A reshaped 6, 4, -1 look like? Yeah, that's actually an interesting question because you already have 6 by 4, which is 24 elements, and you are giving one more elements, one more dimension. It looks like every element of second column of B is covered with every element of second column. Second column. So the second column is here, is covered with second axis. Sorry, second axis. No, B is just a matrix. I'm not really sure. Yeah. Yeah. So Kim Hyun-kyung-nim, so that's not actually true because you get 6 by 4 by 1. Yeah, because you're giving one more dimension. So print H reshape 6 by 4 by -1, and you get like this. So you're adding one more kind of unnecessary dimension to the last dimension. So it's becoming, so everything is becoming its own tensor or its own vector with the element size 1. So it's a bit unnecessary. You can go even overboard. You can go beyond that. Oh, actually you can't. Okay, so okay. Oh, okay, I see. Can only specify one unknown dimension. I'm sorry. Yeah, you can't actually use -1 all the time because in order to infer -1, you need to know the remaining dimensions to actually calculate what the -1 should be. So this should be 1, and then -1, and then you get even more weird looking. So it's a tensor, a vector of vector with element number with one element inside. So kind of crazy looking tensor, but it's just suffice to say you can do it. It's okay that you know that you can do it. Sometimes you may have to do it. So, all right, moving on. Why is my? All right, I'm just gonna erase everything. Something's wrong with my runtime. Edit. Clear all outputs. All right. So we've looked at this. Adding an extra dimension. This is a bit of a trick. So so if you have 0, 1, 2, and then you have column, comma, none, then that's giving you one extra dimension. So it's exactly like what? It's exactly like reshaping with one extra dimension in the end. So this and reshape, this is 3 by 1. It's the same thing. But it's easier to just use none instead of reshaping all the time. So yeah, when you want to do like matrix multiplication, when you're like building a deep learning model and you just need one more dimension somewhere, then you can use none. So quiz, if A has the shape of 3 by 4, how to make it into 3 by 1 by 1 by 4 using why don't you use none only? Like what do we need to do if we have A equals NP 1s 3 by 4, and you want to make it into, you want to turn it into a 3 by 1 by 1 4. Okay, let's try that out. Print A, comma, none. I'm sorry, I should have used the reshape. I mean, not reshape, shape, to see the shape. 3 by 1 by 1 by 4, exactly. So yeah, so what Eunjin Choi and Jung Yoon-jin just described is exactly the same thing. So if you don't use the last column, it means that you're implicitly using all the elements in the last axis or the last dimension. So basically, it's the same thing. If you go like this, then you're explicitly saying that I'm sorry, Shane. You're explicitly saying that I need to take all the elements or all the rows or all the elements in the last axis. If you don't have this, it's the same thing. So yeah, sometimes, yeah, I guess, yeah. weirdly, not a lot of people know this trick using none, but this is super simple. Instead of adding like appending a dimension or reshaping, just simply using none is clearly just a time saver. Okay, and moving on, stack and concatenation. This is this is a very often used feature. Actually, okay, so we're going a bit overboard. This is already 12 o'clock, so I've started a bit late, so I'm hoping that I can go a bit longer than 12 o'clock because we still have some more to cover, and there's final quiz. So if you have something to do, if you have like some schedule at 12 o'clock, you can leave whenever you want. If you have some more time, we can go a bit longer. So stack and concatenation. So we have ones of shape 3, 2, zeros of shape 3, 2, and then there are 3 ways to reshape your matrices, which is VStack, HStack, and concatenate. And let's see what happens. So A looks like this, B looks like this. If you do VStack, that means vertical stack. So you're stacking A and B vertically, so that's why you get this. If you stack it horizontally, HStack, with A, B in order, then you get this, right? And you can repeat it. It can be ABA. So that means like 1 1 0 0 1 1 1 1. Like this much. I mean, like this much was A, this much was B, this much was A. So it's ABA. ABA HStack. And concatenate is a generalization of VStack and HStack. So concatenate, you concatenate, and then you give what you want to concatenate, and then you have to specify which axis you want to concatenate along to. So if this is concatenating along the axis 0, axis 0, if you have a matrix, axis 0 means row, and axis 1 means column. So this is row-wise vertical concatenation. So that would look exactly like VStack here. So VStack and concat axis 0 is the same thing. If you do it axis 1, it will look like HStack, right? And why you need concatenation instead of VStack and HStack is because if you go higher than matrix, if you go higher dimension, like 3 by 3 matrix, 3 by 3 tensor, 4 by 4 tensor, and you want to concatenate it somehow along some axis, then you need to use concatenate. So there's a quiz here. Would concatenating 2 tensors whose shapes are 4 3 2 and 4 5 2 on axis 2 work? Would that work? Yep, that was a very fast answer. Yeah, it'll give you an error. And that's because the first 2 shapes don't match. It's 4 3 and 5 4, so they don't match. So if you want to concatenate a higher dimensional tensor, then let's go with easier ones. One's 4 by 3 by 2, 4 by 3 by 2, and then you print np concatenate A, B along axis 2. Then you get the proper thing. I mean, like this much is all A, and this much is all B. And you have 3 choices that you can concatenate along. It could be either axis 0, it could be either axis 1, it could be either axis 2. Doesn't matter because they all match right now. They all match. Actually, they don't need. This doesn't even need to match. So for example, let's say this is 2 and this is 3, and then you want to concatenate along axis 0. This also works because the axis that you want to concatenate along, they don't need to match. It's the other ones that need to match. So because you can see here that the first 2 elements are from A, and the remaining 3 elements are from B, because you're concatenating along the first axis, which is the, I would say, mini batch axis. Yeah. And then again, you can, if you have 3, 3, and if you have 3 here or 3 here, and then you concatenate along the last axis, still works. You can see that the first 3 are from A and the last 2 are from B. So yeah, just it's easier if you can imagine in your head what's happening here. So because there will be a lot of occasions, a lot of opportunities for you to use concatenation in PyTorch or in TensorFlow all the time. So you want to make sure that you are pretty familiar with that. All right, moving on. It's a transpose. Transpose is a transpose. There's nothing too special about it. When it's two-dimensional matrix, it's a transpose. But when you go higher dimension, if you use a 3D tensor and then you do a transpose, it's a different story, because transposing, it's actually swapping axes. Here, what you did is you swap the rows with columns. That's what transpose is, right? But if you have a higher dimensional tensor, 3D tensor, then you need to specify which axis that you want to swap or transpose. So here, let's see what happens. You have a shape of 432. So it's 24 elements for a shape 432. And then here, we've written transpose A to 1. So that means you want to swap the second and the last axes, 0 to 1, second and the last axes. So that becomes, if you have 4, 3, 2 and swap the last two axes, then the shape would be 4, 2, 3. So 4, 2, 3, and the inside would look like this. So basically, you're transposing here, 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 and here. So you get, it's now rotating 90 degrees. Like, you can go a bit more weirder than that. So you're transposing, you're swapping the axis of first and the second ones, because this 0, 1. So 2 is left alone. You're swapping 0 and 1. So that's like you're swapping the first and second axes. And the shape would be 3 by 4 by 2 now. 3 by 4 by 2. And now it looks a bit weird. Yeah. But yeah, now it looks a bit weird, but still, it's working properly. So sometimes you do need to swap axes. For example, I said that let's say that your matrix 4 by 3 by 2 is you have mini batch of 4 and sequence lengths of 3, and each time point in your sequence has 2 elements. There are some occasions like that. So it's a batch axis, time axis, and the actual sample. And sometimes you want to operate on your time axis using LSTM or RNN. You want to operate on the time axis first. So you need to swap axis in that case, and that's when you use this operation. You swap the batch axis and the time axis, and then you operate on the time, and then you re-swap it back when you do something else. So yeah, sometimes, yeah. So transpose, you need to use it sometimes. All right, now we're moving on to broadcasting now. Was there a quiz? Okay, there was no quiz. Broadcasting. So broadcasting is, I think I explained briefly in Korean, but it's just basically, if you have an extra dimension, then and so if you have if you're operating on 2 tensors and one of them don't match in shape, and if a certain condition is met, then the Numpy will automatically match the shape for you. So in this case, one is a vector, another is a scalar. And obviously, if you try to add a scalar and a vector, it won't work. Mathematically, it won't work. But in Numpy, the scalar is broadcasted, so it's okay. So A looks like this, and B is just 2. And if you add them together, then B implicitly becomes a 3-dimensional vector filled with 2s. So that's why 1, 2, 3, 0, 1, 2 becomes 2, 3, 4, because you're adding 2s in all elements. You're subtracting 2s from all elements. You're multiplying 2s on all elements. You're dividing all elements by 2. So implicitly, B is becoming what? B is becoming 2 by 2 by 2. I mean, not 2 by, it's 2 to 2. So that's what broadcasting is. So even if, I think this actually also works if it looked like this. So what did I just do? Before B was 2, which means that it didn't have a shape. The shape was 0. But this has a shape of 1. It's a 1-dimensional vector with 1 element. So it's a shape of 1. Both cases, they're broadcasted correctly. So in both cases, even if there's no shape, then NumPy will give it a shape of 1 and then broadcast it, match the shape. And if there is already an axis of shape 1, of size 1, then that can be broadcasted as well. So these two are the same thing. All right. In this case, one is a matrix, the other is a vector. So let me just print them out. A is this, B is this. And what happens if you add A plus B? What would happen? Obviously, 1, 2 is added to all the rows here. All the rows here. So it becomes 1, 3, 3, 5, 5, 7. The same principle applies to multiplication, division, and subtraction. So what's happening here is that B is turned into B, which is so B's shape. So print B. B's shape is 2. So there's only one axis, and B's. Let me just make it more clear. B's number of dimension is 1, and its shape is 2. And what's happening here, if you broadcast it, is that internally, B becomes B, reshape 1, 2. So it's becoming a 2-dimensional matrix where there are only one row, and since there is one row, it can be broadcasted into how many rows? 3 rows. So that's what's happening inside. Of course, you can. Just remember that this is the same thing as this, right? Just a side note. Anyway, so this is what's happening inside when it's broadcasted. All right. Moving on to tensor and matrix. So there's a tensor and there's a matrix, and you can see that the 3, 2, and 3, 2 match. 3, 2, and 3, 2 match. So internally, B will become 1 by 3 by 2, and then broadcast it into 2 by 3 by 2, and then the addition will happen. So this is added to here and here, and you can see that it is properly added. Yep. So the quiz is, how can you use none to do A plus B? Pretty easy. That's you do A plus B none colon. It's the same thing. So here was A plus B. This is A plus B none colon. Yeah, exactly. Yeah, Unjin-che got it right. You use none. If you use it in a weirder place, like weird place like this, it would not work because the dimensions don't match. They can't be broadcasted because one is 2 by 3 by 2, the other 3 by 2 by 1, so it can't be broadcasted. Easy. That also works. Yeah, that also works. Let's see if this also works. Yep, it also works. So I said that implicitly the columns are always there. So if you remove one column, that's still okay. If you remove all columns, that's also okay. Good point. All right, so we've gone through all the things that I needed to cover. I meant to cover today. So which is, yes, defining looking at scalars, vectors, matrices, and n-dimensional tensors, defining it with ones, zeros, arrange, random, full, different ways to define a matrix. Indexing and slicing, conditional indexing, advanced indexing, that kind of stuff. Math operations, shape manipulations, broadcasting. So now you're ready for the final quiz, which is this. So let me read it through. So the sigmoid function is given to you, so don't worry about this. So the task is define a function that given M of shape M comma N and a matrix W of shape 4N comma N executes the following. Take the first half rows of M, so first half rows of M, take the second half rows of M, take the odd numbered rows of M, take the even numbered rows of M, append them horizontally. It means like this way, left to right, horizontally. In the listed order, so that you obtain a matrix X of shape what? What is the value of this question mark? If you take the first half rows, if you take the second half rows, odd numbered rows, even numbered rows, and you concatenate them horizontally, what would the outcoming matrix would look like? What would be the shape look like? If the M's shape was M by N. Good point. Let's say that M is always a multiple of 2. Unfortunately, 2M is an incorrect answer because we're taking half rows, which means that 50% of the rows of M. 50% of the rows of M. 50%, 50%. So it would be M over 2. Yep. So M over 2 by 4N. Right. And then you linearly transform X with W so that you obtain a matrix Y of shape. What would that be? So this turned out to be M over 2. So if you transform it with W of shape 4N by N, what would be the remaining shape? Exactly. So M over 2 by N. And then you put the Y through the sigmoid function, through the sigmoid function, and then you need to obtain the sum of the row-wise mean. And what is the value of that? Can you code this? I have a test case, so when you're ready, let me know because I can test it out. I'll give you maybe 5 minutes. So know that this is a bit of an artificial, like a strange, unnatural quiz. But if you know how to do this, you'll have an easier time coding deep learning models in PyTorch. Basically, deep learning is just a bunch of matrix operations or tensor operations. So if you know how to do this, then it's definitely easier for you to adapt to get used to the PyTorch coding, because the APIs of Numpy and the APIs of PyTorch are very, very similar. They're almost the same, actually. Like transpose, sum, mean, max, min, they're all there. It's the same. Concatenation, H stack, B stack, I think they're all there as well. Y 쉐입이 왜 n by 2가? So 여기까지는 괜찮으신가요? 여기 이 하이라이트하는 부분까지는. 네. 그거를 linearly transform. Yes, exactly. Linearly transform is matrix multiplication. So it's a dot product. 그러니까 요 x를 m by 그러니까 2분의 m, 4n로 생긴 매트릭스를 w랑 곱하면은 이제 4n이랑 지워지니까 이제 2분의 m이랑 n이 남는 겁니다. 네. So what's actually happening here is that you linearly transform x to w, so you're actually downsizing your dimension, because it used to be half m, 4n. So it used to be 4n dimension, and then now it's becoming half mn. So the dimension is shrunk into one fourth of its original size. 네, 맞습니다. 근데 m이 큰 m이 네, 첫 번째 인덱스 0부터 시작하는 거 맞아요. 네. 근데 m이 로우가 10개일지 20개일지 모르니까 제너럴하게 짜셔야죠. So what's happening here is, as I said, you're linearly transform x with w. That means that you're shrinking your dimension, and then you're putting it through a sigmoid function. Though, so that makes it nonlinear. So these two rows mean nonlinear transformation, which is the essence of deep learning. It's just a bunch of repeated nonlinear transformation. Okay, maybe a couple more minutes. Yeah, I want to give everybody sufficient amount of time. All right, test input and output. Give me a second. I'll copy paste it here. Oh, okay, that's weird. So this is W, and this is M. And let's see what you get. 나 이미 올려놓았는데요. 아니면 퀴즈 답을 제가 안 푸는 것 같은데, 여기다가 따로. 아, 뭐 몇 개는 풀기도 한 것 같네요. 그러니까 제가 오늘 막 이렇게 지저분하게 한 거 말고 그 오리지널 노트북 올려놨어요, 이미 KLMS. 혹시 그거 말씀하시는 건가요? 여기도 제가 딱히 퀴즈에 대한 답을 달진 않았는데. 이걸 그냥 그대로 올려드릴게요. 혹시 필요하시다면. 네. 근데 사실 퀴즈는 다 그냥 한 번씩 그냥 카피 페이스트해서 실제로 돌려보면은 네, 바로바로 확인이 가능합니다. 2.5287. Okay, that's not exactly what I got. 아, 녹화 파일은 다 유튜브로 올려놓고 유튜브로 네, 저번 것도 올려놨을 텐데요. 네. 네, 모든 수업은 유튜브로 올려놓을게요. Okay, all classes will be recorded and then uploaded to YouTube. 예, 그것도 다 KLMS랑 클래스썸을. Okay. In case anyone hasn't registered themselves on class썸, please do, because next week, from next week on, I'm not gonna post any more things on KLMS. 네, 유튜브 링크는 다 KLMS랑 클래스썸에 다 올려놓을게요. Linearly transform X with W so that you obtain matrix 1. 그러니까 linearly transform 한다는 게 그냥 X랑 Y, W를 행렬곱을 한다는 얘기예요. 그러니까 여기 보시면은 X의 그 형태가 2분의 M, 4N인데 요걸 W랑 곱하면은 W랑 이제 행렬곱을 하면은 2분의 M, 4N짜리랑 4N, N짜리랑 행렬곱을 하면은 이게 4N, 4N이 지워지고 2분의 M이랑 N이 남잖아요. 네, 그 얘기입니다. 그러니까 리니어 트랜스폼 한다는 건 그냥 행렬곱을 한다는 얘기예요. N과 W 예시 한번 더 얘기해 줄 수 있나요? 어떤 예시를 말씀하시는 거죠? 그러니까 여기 말씀하시는 거 여기서부터? 네, 여기서부터 말씀하시는 건가요, 현경님? 경현님? 네네. 오케이. 그럼 마리오님이 해주셨네요. Okay, so far I've not seen answer that is the same as mine. Two, unfortunately not two. It's not a clean number. It's like something point something something something. And the shapes are not even the same among the students, so that's a bit unfortunate. So yeah, some people are posting a scalar value. Some people are posting a two-dimensional vector. Some people are posting six-dimensional vector. Finally, 안재민님. Yep, that's the one that I got. Could you maybe post your code here? 안재민 여기다 코드 올려주실래요 혹시? All right, let's see if that's true. So shape is shape. Actually, if the rest of the students they still want to try out on their own, then please don't copy paste Anjamin's code because that got the correct answer. So the correct answer is, as Anjamin posted, this is the correct answer. And see if you can get it. Just tweaking your code, see if what's wrong. At least let me go through Anjamin's code. So that's A is the first half, B is the second half. All good because you're using shape zero. So shape zero is the size of the rows in your matrix. So size of the rows being the matrix being M, right? So that's if M is 10, then the SH0 divided by 2 will be 5. So it's until 5 till the end, and then skipping the getting the odd numbers, 1 starting from 1 to the end, skipping 2, and starting from 0 to the end, skipping 2. So this is the even number, and then concatenate horizontally, x is 1, and then you do a dot product between this one and the w, and then you put it through a sigmoid function, and then you get the e. All good so far. And then what do you need to do? You need to obtain the sum of the row-wise mean. So row-wise mean being you do a mean of e in row-wise, meaning horizontal, vertically. So that would be x is 0. So you do mean x is 0, and then you print the f shape. And well, I guess this is for sanity check. And then you get the sum of the mean. So that's correct. That's how you do it. And f could have been like this. F could have been. f equal e comma mean x is 0. But that's okay. All right, I gotta end the class here. I have another meeting at 1 o'clock, so gotta get prepared. Is there any last minute question? I will copy paste Anjamin's code and then put it in my notebook. Okay, that's unfortunate. All right, yeah. Let me just copy paste it, and then somehow I'll put it in my notebook, and then upload my notebook on class on KLMS. Because I asked the row-wise mean, so meaning that you want to mean vertically. Vertically mean the axis is 0. 그러니까 그게 그 row-wise mean을 하라고 그랬기 때문에 그 row라는 게 이제 그 행이잖아요. 행. 그 첫 번째 축이잖아요. 그 행렬이 첫 번째 축, 두 번째 축인데 그 첫 번째 축으로 하라는 거 그 mean 그 average를 하라는 거기 때문에 이제 axis를 0으로 쓴 겁니다. 네, 그러면 여기까지 들어주셔서 감사하고요. 오케이, thank you for 행값이 4인 건가? 텐서에서 432 행값이 4인 건가? 그러니까 이제 행이라는 거는 사실 텐서가 이제 4차원이 되면 행하고 열이라는 건 없긴 한데 어쨌든 첫 번째 차원의 값이 4인 거죠. 텐서의 쉐입이 432이면은 첫 번째 차원에 4가지의 엘리멘트가 있다 이렇게 보시면 되는 거죠. 네, 그 텐서의 쉐입이 431이면 첫 번째 차원에 4가지 엘리멘트가 있고 두 번째 차원에 3가지 엘리멘트가 있고 세 번째 차원에 2가지 엘리멘트가 있고 마지막 차원에 1가지 엘리멘트가 있다 이런 얘기입니다. All right, guys. Thank you all for listening until the very late hour, and I'll see you guys next Tuesday. And I'll upload the YouTube. I'll upload the class. I mean the lecture today on YouTube, and also share the Python notebook on both KLMS and Classroom. But still, please do register yourselves on Classroom because so that I don't have to do the same work 2 times. All right. Thank you very much. Bye bye.